We have so far assumed that mobility is independent of electric field and is a constant, but that may not be the case because of two specific reasons. First is variation in mobility with gate voltage, and the other one is the effective carrier mobility decreases as the carrier approaches the velocity saturation limit. We have actually studied similar topics in the first unit, Basic Semiconductor Physics. This is a graph of mobility with electric field in which we can observe mobility is independent of electric field up to certain value of electric field. However, as the electric field strength increases, then the mobility will begin to decrease. We also know drift velocity is equal to mobility into electric field, and we can also draw the graph of drift velocity with electric field. These graphs are meant for simple semiconductor block, but we are studying MOSFETs which have a specific arrangement because of which we cannot use the same formulas here which we have used in first unit. Now observe the transfer characteristics graph of N-channel MOSFET. Focus particularly in the triode region. We know the equation of drain current. If we assume the drain to source voltage to be very small, then we can drop this term such that the drain current becomes approximately linear with gate to source voltage. From this relation, we can say the curve in the triode region should have moved in a linear fashion ideally, but practically this is not the case. The current begins to saturate, and this occurs because of saturation in drift velocity. These two simple graphs are actually divided into three regions. If we try to relate it with MOSFET operation, then this particular region can be said to be representing the ideal behavior, and these two non-ideal regions will be considered separately in non-ideal effects of MOSFET. This will be considered mobility variation, and this region will be referred as velocity saturation. Let's start this lecture with the next non-ideal effect, which is mobility variation. Consider an N-channel MOSFET. For operating a MOSFET, we require two potential drop, one across gate to source and the other across source to drain. These two potential drop obviously results in electric field in different directions. Based on the direction of resultant current, which is drain current, these two electric fields are named. The electric field in the direction of current is referred as longitudinal electric field, and the electric field which is perpendicular to drain current is referred as transverse electric field. In this lecture, we are interested only in transverse electric field. So to avoid confusion, we can remove longitudinal electric field and can rename transverse electric field to effective electric field. This effective electric field is responsible for creating inversion layer by attracting free electrons at the top of semiconductor. When we apply drain to source voltage, then electrons begin to move laterally. At lower gate to source voltages, there is no problem. But when gate to source voltage becomes high, the high effective electric field becomes problematic as it begins to attract the charge carrier so strongly in the transverse direction that their longitudinal movement begins to get restricted. Free electrons are more strongly attracted to the surface, resulting in decrease in mobility, which further results in drift velocity saturation. The drift velocity does not increase linearly with the electric field because of mobility variation within the MOSFET. This whole phenomena is referred as surface scattering. We have studied two types of scattering in the first unit, Basic Semiconductor Physics, which are lattice scattering and impurity scattering. And this is the third type of scattering effect which occurs in MOSFET. If there are fixed charges within the oxide, the mobility degrades even further. I hope you can imagine what is actually happening here. Now we will see some formulas. The effective electric field is equal to modulus of charge present in the depletion width per unit area plus half of charge in the inversion layer per unit area whole divided by permittivity of the semiconductor. Magnitude of charge in the inversion layer per unit area is equal to capacitance per unit area into applied gate to source voltage minus threshold voltage. At threshold voltage, it is assumed the charge in the inversion layer is 0 and increases when the gate to source voltage is increased further. The most widely accepted formula for effective mobility is equal to mu naught into effective electric field divided by E naught raised to the power minus 1 by 3, where mu naught and E naught are determined experimentally. The effective inversion charge mobility is a strong function of temperature because of lattice scattering. As temperature decreases, then the effective mobility increases. Similarly, as gate to source voltage increases, the carrier mobility decreases even further. Our next and the last non-ideal effect is velocity saturation. Assuming constant mobility means that the drift velocity increases without limit as the electric field increases. Obviously not true, the carrier velocity increases until the ideal current saturates with increasing electric field. Current saturation ideally occurs at pinch off voltage, which is equal to gate to source voltage minus threshold voltage. However, velocity saturation can change this condition, particularly for short channel devices. Modified saturation current will then becomes depletion width into capacitance per unit area into overdrive voltage into saturation velocity. If we increase the gate to source voltage, then saturation velocity decreases. This happens because of vertical electric field and surface scattering. Similarly, we have modified transconductance, which is equal to depletion width into capacitance per unit area into saturation velocity. This transconductance becomes independent of drain to source voltage and gate to source voltage when velocity saturation occurs.